I'm very happy to see you all here. I see more than 100 people join so far, and I've got great confidence for what we can achieve while we are here as part of this Open Power Academia and Research webinar series. And today we have Dr. Linton Ward, IBM Distinguished Engineer, and worked for IBM nearly 38 plus years, and with lots of the IBM the solutioning skills as well as hardware skills. And our second speaker is Dr. Athirai Irespan, Assistant Professor from University of Washington-Tacoma. She also joined as part of the webinar today. And today's session will be recorded and shared. And about Linton Ward, my colleague as well as the IBM Distinguished Engineer, is very passionate about creating and technology solutions to real business challenges. And he has been working for IBM, as I said, 38 plus years, and has been working in a cognitive workload solution development on open power system and a bunch of the power systems too. Linton, please go ahead and start your presentation.
Okay, I'm going to share my screen. Oh, there we go. So I'm going to go into full screen mode. Tell me if we're working correctly, Ganesh.
Looks good. Please go ahead.
All right, beautiful. Okay, thank you, Ganesh and everyone. Thank you for taking the time today with us. What I'm going to share today is not just my work, but the work of many people, both within IBM and as partners. Because of the nature of what we're doing here, it really is a team sport. The motivation for this work is that we saw the need, the worldwide need that everybody's very familiar with, to respond to this literally global crisis. And we felt that Power Systems and IBM Storage have capabilities that will be very useful in the fight. So this is not a sales presentation. This is a presentation about the capabilities that we have brought together that we see as relevant in the high performance data analytics world. And I'll talk about 6 different solution categories. I will talk at a very high level. Unfortunately, you have had presentations from the Summit team at Oak Ridge. You've had presentations from others such as Clarice on some of the medical imaging. So you've actually seen some of these results in detail. Some of the others, maybe we should have a follow-on which describes those as well. I also need to point out that this is not the, I'll call it enterprise response. So, those folks who need to run more capacity around Epic electronic medical records or drive better resiliency of their systems in these days, I'm not trying to cover those. This is really about the relevancy of OpenStack, OpenPOWER, and the capability, the very good work that's being done by researchers around the world. So with that, I will just share just a few of the IBM collaborators. Dr. Frank Lee, whose background is in genomics, has been driving this sort of thought for a long time. Many of you may know Frank from that work. I think I saw that Clarice Taff-Hedgeland is on. She has been leading one of the plays. And so some of these folks will speak up if we have questions in their domain as well. I just want to highlight one partner, Mike Kolenko at Nova Systems, has been collaborating around the data fusion thought, and I will describe what that means a little further in. One of the challenges that we have, and I'm sure we have a mix of direct line researchers as well as those who support researchers, so infrastructure builders, IT architects. One of the challenges we have is describing the infrastructure importance to the actual consumer or data scientist or research environment. Because these are typically different domains in many organizations, these are things that where the skills or the dependencies are different. What we've attempted to do here is to capture the essence of the impact on what I call the workflow and the data flow. So because of immense advances in sensor data collection, generation around genomics and say cryo-EM, it changes the need so that humans can actually couple into the workflow required or made possible by these new instruments. So it's a very exciting time in that regard. So the question is, you know, if bandwidth and more performance have a value, does it allow us to cross thresholds so that I can now work in a different way? Can I do pharmaceutical research and discovery in a different way than I did previously? So the 6 plays that we are describing today, and I'll talk highly here and then in more detail in a moment. Traditional genomics, the generation of biomarker data, the relevance to so-called precision medicine, et cetera. I'm sure you've all seen the press and the confusion among policymakers, as well as the very aggressive response from the researcher community. IBM is proud to be able to make resources available through both partners and within IBM to accelerate the R&D discovery. So when we think about the traditional state of medical discovery, we're talking nearly decades in order of magnitude. With the level of increase in capability from both the instruments and the IT infrastructure, it allows for a substantial rethink of the capability. We'll talk about how in the genomics workflow, for example, you know, I move from 1 or 2 sequence tasks to a high volume data factory where I can now begin to think about sequencing populations. I can begin to think about the kinds of work you're seeing in the press where we're looking at the variety of strains, the geographic distribution, et cetera. So you've had the talk from Summit. So the sifting from compounds of the order of thousands down to a few tens, molecular simulation and molecular dynamics, we call it. Biomolecular structure, you're familiar probably with the Nobel Prize that was won for cryogenic electron microscopes. And so the ability to reconstruct those 3-dimensional atomic images is faster and enables an improved workflow there as well. I use the term diagnostics in the upper right. This is really AI in digital pathology, digital radiology. So we'll talk a little bit about how that is coming to bear and can play in this medical response. The term we call data fusion and artificial intelligence, the ability to combine diverse data types, gives us the greatest context and best specificity for looking for answers. So whether you're a researcher in the healthcare field, a policymaker, being able to integrate diverse data types, including text, as well as relational tabular data is very critical. So our partner Nova Systems, as well as partners H2O, had built out some interesting capabilities that allow for acceleration of those discovery and manufacturing, in fact, events. I will describe an example of its use both in discovery and manufacturing. Quality inspection, you've probably seen the visual inspector. I know Clarice did a presentation. So the ability to use both open source and tools like IBM Inspector to accelerate the model building and inferencing of quality images in manufacturing. So as a part of the overall quality life cycle, the ability to drive new capabilities. So this is not my favorite chart. However, I would like to share with you kind of where these play. You've seen probably in the press the race for both therapies and vaccines. Therapy meaning an antibody or some chemical compound that prevents the coronavirus from actually infecting patients, that take that spike and cover it in some fashion to prevent the biochemical reaction that it is having. So molecular simulation, biomolecular structure to understand the shapes of proteins and lipids and other things, the role of genomics in the biomarker, as I said, you know, both in the early stage and in the late stage. So I like this chart in one sense in that it shows a traditional timeline of moving from, you know, thousands of compounds over a period of almost a decade down to getting into clinical trials. And of course, we've seen in the press that clinical trials have begun for some repurposed drugs and will begin shortly this summer or in the fall for new therapies or vaccines around COVID. So as we look at this overall life cycle from compound discovery to the precision medicine biomarkers down into all the way through manufacturing, we believe that AI, high performance data analytics can play a substantial role in assisting with this acceleration that both policymakers and researchers are going after in this fight. And Ganesh, if you don't mind, as we go along, if you could keep track of the questions, I feel like it would be helpful to, because since I'm focusing on the charts, I'm not really focused on the questions that may be coming in via the chat. But feel free to break in, Ganesh, if you need to.
Yeah, sure, Linton, sure.
Okay. So this chart is actually from Frank Lee. Dr. Frank Lee it's a very good example of the kinds of challenges that we face. So in my mind, as I look back at the capability of, say, genomics from Sanger, single genome sequencing approaches to the capability for high throughput or so-called next generation machines and onto the yet next generation machines, the lowering of cost, the acceleration of, say, genomics has produced such an incredible amount of data that we're looking at now petabytes to couple the IT analytic capability to the throughput of now high throughput at, I won't say low cost, but at improved tolerable cost sequencing infrastructure. That trend will continue. So when we look at the improvement of sensor instrumentation, scientific image instruments from genomics and electron microscopes, we are being buried in data. The open source world is tremendous for the advancement of capability at a rapid rate. The downside of that, of course, is that we now have so many applications. And so can we create a platform that generates a general purpose capability for high throughput multi-tenant environment on top of optimized infrastructure for this variety of applications? And I might pause there and just comment that John Cohn, our colleague at MIT with the Satori cluster that IBM gifted to the university, John's an IBM fellow, and he's kind of admonished us. He said, hey guys, you haven't really told the world well about the capability of OpenPOWER with the open source ecosystem it is truly phenomenal. Researchers are pleased with the performance and the ease with which they're moving their applications over. So we're working on that. The notion of tool sets and integration, you know, in this medical field, as is true for most fields, having a capability as a standalone thing isn't really good enough. It needs to integrate into the workflow. It needs to integrate into existing applications. And so can I take this open source capability and now integrate it in with a workflow without a vendor lock-in, without an overly rigid infrastructure? Performance and cost kind of go without saying. I won't highlight that here. Let me just give you one example from Washington University and Vanderbilt. I think we'll have them share, if they have not shared already. I know that we've been talking to Carlos at Vanderbilt. And so this idea of the digital world, so, you know, much of pathology and radiology has already moved to sort of a digital basis. Obviously, MRIs and CAT scans started life in the digital domain, but even two-dimensional X-ray images, et cetera, are pretty much predominantly in the digital world. So once I cross into the digital world, what is the role of computational pathology and radiology? What is the role of artificial intelligence in improving the workflow, not just of a single pathologist, but of peer review, of second opinions, of the ability to enhance or augment the capability of a human? So we see this capability for leveraging open source tool sets as well as value add tool sets in medical imaging, just as one example of this overall capability. Let me pause and talk a little about the infrastructure, since I know we have a number of what I call builders, you know, architects and implementers of IT infrastructure. Perhaps you provide solutions in this space. The architecture that Frank has laid out and we have laid out for other domains, Frank has adapted it well for this medical life science world. So there's a set of tasks, workflows, applications, open source codes, models that are domain specific, et cetera, is the second layer of the stack, if you will. But now I need a place where I can run that stuff on the infrastructure. So physical resource management, orchestration of the workflow, et cetera, and then managing the vast amount of data underlying that. I call it the data plane. We use here the term data hub. The reason I like data plane is if you look at a diversity of applications, I need to be able to get to that data from a variety of protocols, whether it's Hadoop file system or NFS file system. The ability to get at the same data in a native way allows me to optimize the workflow of the researcher or of the analyst or of the data scientist. So this is the overall architecture I'll talk a little bit about in more detail. Physically, this is implemented as OpenPOWER servers with storage. We use the Spectrum scale file system. However, we know many places use other file systems, parallel or scalable file systems. And the same is true of the orchestrator. We use the IBM Conductor or LSF, depending on your flavor, for running these kinds of applications. This looks a lot like a high performance computing infrastructure. However, it is now incorporated the data analytics and artificial intelligence capability. So the application and tool layer, and my hat's off to the collaboration between IBM clients, partners, and our open source team. You can see the Jupyter notebooks in Python, our collaboration around Anaconda and the Conda channel for Power has provided a number of very, very strong capabilities. You see the R language there. working and collaborating with a customer that has been driving for R to support their scientists, data scientists. We've been able to support R through the conduit channel on Power. We just did a collaboration with the team at MIT around Julia compiler. So we have now the capability moving forward for Julia with the jump optimization capability on Power as well. And so there's a rich and growing, depending on the domain. So you see TransSmart, some of the genomic capabilities here as examples. Each domain, of course, has its own ecosystem. We have brought this together based on a couple of OpenPOWER servers. You see OpenPOWER on the left side that allows this thing to be integrated to go after the variety of medical or life science applications. I won't speak in detail, but there is the capability using OpenPOWER servers to configure these high performance computing types of compute as well as storage solutions as we describe here. When we look at the overall data world, what we're seeing is a very substantial shift going on. As you all know, Hadoop was all the rage for well over a decade. However, people are beginning to see that, you know, copies of data going to disk in between job steps has become somewhat painful and constrained. What we're seeing now is a shift to a computational environment which augments the data lake or the relational database world. So a data layer and even partners, vendors like Cloudera have now stated, because of the move to cloud, the decoupling of compute and storage is really critical to go forward sorts of architectures. So this idea of driving the data analytics grid, if you will, this AI grid, if you will, which extracts data. With one partner, we have built out a tool set that uses open source components to pull data out of Teradata, for example, at high bandwidth, so that the data science team can daily get the most fresh operational data, but using an open source tool set to manage the data flow. And based on that, allowing for a diversity of user types. This really is the vision, moving from sort of single thread, single user, single task, to the ability to support a multi-tenant workflow where collaboration can shine, really is what is accelerating these workflows. We kind of see a few stages to this decoupling. Decoupling of compute on the left side, creating, I'll call it my data plane or some sort of shared storage tier, which requires a parallel file system, requires multiple protocols, as I mentioned, and then the creation of an AI hub. We see this playing out over and over again in client architectures to enable the kinds of science, the kinds of research, the kinds of analytics that we see here. So this progression from tangled compute and storage to the recognition that operational data is always going to want to reside on a different infrastructure from machine learning and model training kinds of infrastructures. They're just different by nature in terms of availability, speed, et cetera. And so we see this progression playing out in many places where we rationalize the underlying infrastructure. We also see researchers who have, you know, a multi-million-dollar research instrument, but are storing the data on, let's say, a USB drive that does not enable metadata location, does not enable the kind of shared data plane that we're describing here. So we see both in the enterprise side and in the research side, the need for driving these kinds of architectures that really optimize the workflow, improve time to discovery, time to value kinds of benefits. Let me go into a little bit more detail on these 6 plays. High performance, let me just see here. Genomics, molecular fit or molecular dynamics, the cryo-EM, you know, literally the amount of data being generated by the image reconstruction is phenomenal, terabytes a day. But the ability to now do a fast reconstruction on an image to tell if the sample is going to produce beneficial data in a very short period of time before the sample gets destroyed in the instrument, before my window on the instrument goes away. So it is changing the workflow. I gave you the example of how genomics is moving from single to high volume. Biostructure is moving to this ability to detect immediately. Medical diagnostics, the ability to augment human intelligence for pathology, radiology, dermatology, the ability to integrate data to overcome frustrations, and then medical manufacturing quality. Manufacturing in this case means both the mechanical medical devices as well as pharmaceutical manufacturing, the ability to make decisions around a manufacturing lot. I'll show you an example of that in a moment. Here's an example of Sidra. So Sidra has moved from sort of, to use Frank's metaphor, from the dusty road of, you know, single-threaded genome analysis to population studies, high throughput, high volume. And so we coined the term the Data Insight Factory to support the precision medicine efforts there within the lab at Sidra. So what we're talking about here is immense optimizations. I won't talk in detail. I think some of this has been presented to you before. The idea of taking a high performance computing code and changing the game by making its throughput, its response time much faster. So that's, you know, a single job, and then with scale out of the compute servers with a good resource manager allows us to get that high throughput data factory. Here's some other examples, unoptimized on the left, optimized on the right. You can see that getting down to a few hours instead of a good chunk of a week. So within the daytime, you know, going back for decades, we talk about in high performance computing, the response time of a batch job crossing thresholds. Does it take multiple days? Can I do it overnight? Can I do it during the day? Can I make 2 runs to iterate during the day? Can I get it to run while I'm at lunch? Can I get it to run over a coffee break? These all change the way I think about the data, the way the human interacts with the results of simulation or sensor analysis. So these are all positive in terms of the workflow change. High resolution microscopy, spending $12 million on an instrument to then attempt to use a laptop to analyze the data. We believe that having the IT instrument to support the cryo-EM instrument is the right way to go. You've seen probably results from the NIH, Texas, Duke University, and others around images of the coronavirus all being generated with this sort of Nobel Prize winning technology. This is a very fluid field. We expect the applications to continue to grow and develop. We expect instruments to get better, higher throughput, putting even more demand on the human analyst, the researcher, as well as more demand on the IT infrastructure. For some reason, it's not, there we go. So the idea of taking scattered electrons, which may each give a piece of an image, and then reconstructing them into a particle 3-dimensional image is a fairly, has been a fairly time-consuming job. Codes like Rely On, which incorporate Bayes statistics to enable probabilistic, most likely assemblies have reduced the amount of human intervention. We expect those kinds of mathematical method improvements as well. Maybe you're leading the research in this area yourself. So we see that image processing capability will take advantage of the accelerated compute and will fundamentally change the way we do science. Molecular simulation, you saw the work from Summit and others around the world going from thousands down to 70 or 80 compounds. So there's been plenty of articles there I won't talk about. We have optimized our open source team. Thank you, Rusu, has optimized a number of these codes on Power. And so what we've done is to optimize them. And I have to say that it's NVLink and the GPU connection, and hats off to NVIDIA for all the work they've done there, both in the technology and in the software stack. But often we see the value in high memory bandwidth, high IO bandwidth of the compute node. So when we talk about the benefits for things like cryo-EM, the ability to get random IOPS out of memory at high speed is very critical to success. So this is an example of a fit simulation. You know, what does it take to fit a protein into the binding sites that are causing this disease to take over a human cell and instead bind something else? So we're looking at, you know, van der Waals forces and atomic analysis that allow us to really understand how these dynamic processes, and with the capability, you know, that scales all the way down to the single server as well as up to the over 4,000 servers in Summit, we have the ability to accelerate this kind of drug discovery for the fight. Medical imaging, as I mentioned earlier, is in the process of development. For those of you who are in medical research or even bioinformatics areas or computer science around imaging and diagnostics, this is a tremendously exciting area because we are on the cusp for lots of things, you know, dermatology, radiology, pathology, as well as ophthalmology, dentistry, other things. The need for, you know, faster results, lowering the cost of the image reconstruction, identification, et cetera, is a very exciting area. I invite you to join with us. We believe that the research world will drive these advances. IBM is unlikely to pursue, you know, certification for the drug administrations worldwide for these types of algorithms. So we envision that with OpenPOWER capability, we will see the basic capabilities with open source developed, proprietary value add codes as well. But by and large, the methods, the numerical method as a device or software as a device that's being discussed by the US Food and Drug Administration, those kinds of certifications are more likely to be pursued by partners. So there's a tremendous opportunity here as this field begins to really take off. Obviously, given the cause and the pathway of this particular virus, the need to understand the impact on the lungs, acute respiratory distress syndrome, you know, what is the tipping point, what's the cytokine storm do, and all that sort of stuff become very critical. So we believe radiology will be a critical part of understanding the progression of this disease. So let me talk a little bit about data fusion. So what's data fusion? The notion of taking 20,000 documents. So we worked with Dr. Mike Kolenko at Nova Systems, and I'll show you the link. So Mike has put up a portal for the general public. We will shortly release a portal for researchers to gain access to these tools built on Anaconda, Python, Bokeh, Elasticsearch, open source text analytics and data analytics tools. Mike and team at Nova Systems have built out their own stack using the open source capabilities. And they will prefer to run best on OpenPOWER because, as I said, the memory bandwidth, the IO bandwidth, the ability to build indices faster, drive this coupling of fit for purpose compute with the capability built out on open source. So if you're in research and you want to build your own tool set, we can talk about the open source tools that are available to do that. Let me give you a couple of examples. So here's an example of data fusion within the pharmaceutical world, from clinical trials to production to distribution, leveraging both text, say EMRs, as well as known criteria of drugs, drug candidates, known criteria of sensor data, and the like. So this notion of data fusion gives me sufficient specificity with the right context around the numerical data, the qualitative data in the text, to allow for decision-making beyond what purely numerical analytics might provide. In the production sense, the notion of, I'll just highlight the product release cycle, the ability to integrate with the manufacturing data system as well as others. I will show you the number of data sources required to be integrated, and treating the lab notebooks, the manufacturing notebooks, like an EMR, as well as looking at FDA review data, looking at other industry data, bringing that together accelerates the time to resolution for a lot failure investigation, allows for better or more improved quality development process. So here's an example, and I apologize for the font. I don't really expect you to read the details of this chart, but you can see the number of data sources for quality, manufacturing, root cause investigation, just for making the decision, should this lot of a pharmaceutical product be delivered to the shelves, or does it have to be destroyed? So that decision requires the integration of vast sources of data in a timely fashion. It takes longer to make this decision based on the collection of data historically than producing the product. So this idea of accelerating decision, even in the manufacturing process, and this of course can be applied more broadly than in pharmaceuticals, but I wanted to highlight that case today. This is the link for the systems. I was gonna show you a little bit of the dashboard, but unfortunately I'm kind of running out of time, and I don't want Ganesh to give me a hook here. So I just want to make sure you're aware that the consumer dashboard is available. You can go there and play with this. You can look at worldwide data, the CORD-19 data sets of 20,000 plus documents can be analyzed with text analytics, as well as other statistics from, say, Johns Hopkins and other places. Now, I understand that many places have put up dashboards, but I wanted you to be able to see the capability that's being driven from the IBM cloud on an AC 922 with the stack from Nova Systems. So this is what the NoviLens appliance does. It's built out on an IC 922 data fusion, meaning a variety of sources, pre-treating that data so that I can now create truth tables or fact tables that I can generate questions. So the entire appliance is built around the decision maker, the researcher, the medical doctor, the librarian, the business analyst, to avoid the need for a massive data science project, programming project. So building out decision-making tools that a non-data scientist can use to create actionable decisions. So we're shortening the distance between decision and raw data with this kind of capability. Many of you are familiar with driverless AI. It's another tool that is being actively used within the medical, pharmaceutical, device manufacturing world for machine learning modeling of quality control data, as well as other types of data. You know, statistical analysis of populations for preclinical trials, looking for outliers in population statistics, whether it's manufacturing or in the public. The visual inspector capability, I won't talk a lot. I'm sure you've seen this before. The ability to integrate from back-end training out to the edge device and pressing the same model through all these capabilities for, whether it's a medical device inspection or some other type of quality inspection, we find a very substantial value for this workflow. And so here's the visual inspector product integrated with an iPhone that allows the standalone inferencing of a quality product in the midst of the diverse defect modes and mechanism. Clarice did a nice little demo using some parts she bought from an AutoZone store showing defective parts. I thought it was very clever. I'm going to skip this chart and then wrap up. Just to bring this back to infrastructure, so the IC922, the AC922, we are using underlying these solutions, built out into clusters, provided resource management and storage around them that allow us to build these. I show this not because I want you to necessarily buy one of these, although, you know, I don't think IBM would mind if you did, but based on our OpenPOWER partner Wistron, the ability for you to craft your own solutions, the ability to craft or do research on a research instrument of this type, we think are very significant. I should mention storage, whether it's sensor data from genomics, whether it's simulation data and integration with molecular dynamics, data fusion for text analytics across the board, from research to manufacturing. We believe that storage is a critical play, not just because of the capacity, but the ability to find things, the ability to now incorporate metadata into the decision-making work product. And so the ability to integrate data from Spectrum Discover or such tools that allow us to now take image plus metadata plus an electronic medical record. You know, it applies across the board. We've talked to retailers where I need to have an image of a product, but I need to have metadata for the description of the product. And if I look at what do clients like, from textures to colors to design to style, this ability to combine multiple data types is very powerful, and I believe will be the center of future advancements. So we do believe in scalable storage. We're very pleased with the results from Elastic Storage Server based on the Power servers and the very dense or fast type of storage backend. We talked about the metadata before. I won't go into details. We are looking at integrations with Spectrum Discover, nice product out of the storage team that allows metadata integration with the data itself. And now metadata becomes data, if you will. And so that we know something about the images or the quantified data, now we can get some context. Where did this data come from? What other things were going on? What else was presenting with the patient when I look at this image? I'm going to skip this, but we do have archive capabilities. And then the overall open source at the center of the page here. Hats off to the open source teams, both folks like Chris Sullivan at Oregon State, as well as others, as well as those in IBM and the many communities that are now supporting the Power architecture. Tremendous amount of progress there. You know, that open source ecosystem will be with us for a very long time. It is the future. and then building out value add capabilities on top of that. So the call to action, I think, from this is, you know, researchers are really leading the way, whether it's the AI for diagnostics. You know, there are already many startups who are harvesting concepts and ideas coming out of research. There are federal agencies, both within the US and worldwide, that are driving these kinds of advancements to fight the next one. I did a timeline showing the number of diseases, pandemics, and plagues that have gone because of global travel, the greater degree that humans are encroaching on the animal kingdom. I believe that we're going to see more and more of these viruses. The rate and pace of these things has picked up because of the factors I mentioned. I think this is a fight that's going to be with us to stay. I think it'll be, fortunately, some fundamental changes in the way medical treatments are developed, both in time to value, time to market, and in isolating compounds from thousands of candidates very quickly. So with that, Ganesh, I'll pause. Didn't quite give you 15 minutes, but I was close given our 1 minute or so late start. So Ganesh, maybe you want to open it up to questions, comments?
Yeah, sure, Linton. Thank you, Linton, for the very detailed presentation and sharing your experiences using POWER9 OpenPOWER systems. Participants, any questions for Dr. Linton? Any questions?
Maybe we'll solicit some comments. I know that at least a couple of collaborators are on. If we don't have questions, maybe.
Hey, Linton, this is Terry. I'll provide some dialogue if you like.
Okay, go ahead, Terry.
Yeah, and hello, Ganesan, and a couple of others. Our Gaia, my friend in Minnesota or Wisconsin. So I've been working with Linton on this project of life science solution-oriented architecture with me and Frank and others. I'm a HPC AI sales leader for North America or US. And in particular, I want to tell you that this cryogenic electron microscope is really revolutionary. And just today, the one set of daily analyses generates 5 terabytes of data a day. You can do the math. There's a new instrument coming online that's going to do 4K video and data. That's going to double and triple the load. So there's both a storage and a server problem. How do you store it? Where do you put it? How do you find it? And then how fast can we produce results from the data? And so this just blows up. And the same thing is happening with genomics and other molecular simulations and other things, just due to the sheer nature of the amount of information being collected. So the message at IBM is time to answer, meaning, Mr. Customer, is it important if you can do things 2 times faster, 10 times faster? How will that affect your outcome as either a business unit that serves scientists or as the scientist itself? So we'd love to tell the story and talk to anybody and everybody about it, because until you spin it in time to answer realm, people just think about bits and bytes and cores and IO and things like that. But when you put them all together, it makes a difference. So that's my speech, Linton, and I'll stop there.
Oh, thank you, Terry. Thanks for joining too. Linton, there is a question on the chat window. One of the persons is asking, for COVID-19 to diagnose the disease, how NLP works?
Okay, yeah, that's a great question. We do have the dashboard, which will give some insight. So, you know, a month ago, a little over a month ago, the COVID-19 data set was made available. And if you can imagine, already, in just a few short months, we have some 20,000 research papers that are published that are relevant to the COVID-19. Now, we now know that COVID is a SARS-like disease. So there's been plenty published from the SARS outbreak a few years ago. So there's a lot of pre-existing information. So the question is, when we look at a research domain such as the molecular dynamics simulation of protein fit, for example, you know, what relevant documents are there? Well, a human would take some time to read through 20,000 documents. So the ability to localize that. When we think about the symptoms, quite honestly, when I read the press, I get a little bit confused about what the symptoms are. Even with a known treatment, say diabetes, if you look at some of the blogs and forums and medical pharmaceuticals around insulin, for example, you see side effects that people talk about. Sometimes those side effects are irrelevant and sometimes they are. Being able to pull out the text and the context of those symptoms will help researchers begin to hone in on what the real symptoms are, the signs, if you will. What is the progression of the disease based on much more data than the specific patient that an MD is looking at the moment. So that's a very important and powerful thing. If you know, whether it's genomics, one of the interesting things of innovation in this space is it's the combination of these disciplines that is bringing tremendous insight. So genomics plus clinical medicine, or you know, the clinical piece, the simulation piece plus the genomic piece to look for biomarkers. So I think this integration theme will drive innovation. And we could follow up if anybody's interested in having a more in-depth discussion on the NLP thing. We'd love to have that conversation and we can show some specifics. I just think we're going to run out of time before we could do that on this call.
Yeah, go ahead.
Hey, Linton, I have one small question. So, just out of curiosity, I'm trying to understand that. Do you have any other strategies rather than deep learning that you are applying successfully on this COVID-19 data set? Maybe CORD or maybe some other vaccination or something. For example, like let's say some kind of statistical learning methodology or something else that is being expedited with POWER9 or something. Do you have any type of data?
Well, yeah, I think it's just a number of, so there's some machine learning behind the data fusion capability, which is more conventional, not the deep learning stuff. And we could have a conversation with Mike, Dr. Kolenko, around what they're doing there with regard to the word vectors.
So Argo, another comment that the genomics is generally not a deep learning function. The molecular simulation may or may not be. So there's deep learning around, but the fact that you can speed up all these technologies with the technology we have with the bandwidth and cores and memory IO, all that stuff facilitates everything. Data AI is equally advanced. Does that make sense?
Yes, sure. Thanks.
Sure. I do see some questions in the chat window, but in interest of timing, you know, let me collect those questions and send it to Linton later. Linton, thanks again for your wonderful presentation, and thank you. And now let's move on to the second presentation. as part of this OpenPOWER webinar. Professor Athirai Espani, Assistant Professor at the University of Washington, will be sharing about leveraging GANs for semi-supervised test classification on POWER9 system. And she got, recently the access to one of our, the university partner, University of Oregon, and she experimented, last 1 month, with her application. I welcome Dr. Athirai to start the presentation.
Thank you, Ganesan, for inviting me to give this talk. And thank you everybody for joining this talk. That was a wonderful presentation, Dr. Linton. I'm just going to follow up on on some of the use cases that Dr. Linton described. So I will be talking specifically on one use case with regards to NLP and how the POWER9 systems are being used for this particular NLP use case. So let me share my screen. I hope you can see my screen.
Yeah, go ahead, Athirai.
Okay. So this talk is going to be focused on leveraging generative adversarial networks for semi-supervised text classification. So this is the agenda for my talk. So let me give a brief overview of why this piece of work is important. We all are in the challenging time of coronavirus, and it's really taking a toll on all of us. So one important problem that everybody around the world faces is misinformation. I just borrowed this picture from the internet. It says that eating bananas prevent coronavirus. Warm weather kills coronavirus. There are several other hypotheses surrounding coronaviruses on the internet. Which one of them is truthful? Which one of them is false? Nobody has verified these hypotheses. Neither there is a vetting process for the information that travels around the internet. This is not only the case for coronavirus. Information regarding several things are not vetted, neither they are scrutinized before they are shared online. So misinformation can be in the form of reviews. It can be in the form of posts, Facebook posts. It can be in the form of tweets in Twitter. And they tend to be trending unidentified for several days and weeks, and they are still staying online. So we are in an era of misinformation, so as to say. So what my group is trying to do, we are just taking a small step in identifying this misinformation and promoting a trustworthy online platform. Specifically, we are using generative adversarial networks to identify a specific type of misinformation called as opinion spam. So let me just talk about what opinion spam is. So opinion spam is another name for fake reviews. So we've all have purchased products using Amazon or Flipkart, and we have given reviews based on our experience with the product. Sometimes the reviews can be given by your friends who just want to promote the product. And sometimes the reviews can be given by the competitor who wants to just demote the seller. So we do not know whether the reviews that we give are authentic or they are fake. So that's what opinion spam is. So in our approach, we just target to identify a specific type of misinformation called opinion spam. And how we are trying to do this? We have developed a machine learning model. So this machine learning model, when given a review as the input, will classify the review to be either spam or non-spam. Spam being that the particular review is untruthful or fake, and non-spam telling that the particular review is good enough. It really represents what the product is. So there are some challenges in developing such a machine learning model for classifying opinion spam. The first challenge is the availability of ground truth labels. Let me just describe what ground truth label means. So whenever you are developing a machine learning model, you need to have training data. Specifically, when it is a supervised machine learning model, the training data should also have ground truth labels. Let's say, for example, this is your training set. So you have your reviews and your ground truth labels. So your training set is going to be review 1 and whether it's spam or non-spam. Review 2, whether it's spam or non-spam, and so on and so forth. So these labels, these labels are of spam or non-spam, they have been identified by experts in the field. So to identify these labels, the experts in the field are given the reviews and they have asked the expert to classify whether these reviews belong to the spam or non-spam category. So only few such labels exist. You can imagine the number of reviews that are available online. And if you ask the experts to classify each of the reviews as spam or non-spam, it's going to take a lot of time and a lot of money. So getting the ground truth labels for the reviews is a problem and it's costly. Subjectivity is also a problem while acquiring ground truth labels, mainly because a review which looks like spam for one expert may look like non-spam for another expert. So there is a problem of obtaining ground truth labels in this particular domain of opinion spam. However, though we don't have ground truth labels, there is an abundance of unlabeled data. There are a lot of reviews available online. So unlabeled data or reviews without labels are available abundantly on the internet. And in our approach, we plan to make use of both the limited data with ground truth labels as well as unlabeled data. One more challenge in building this machine learning model is that most of the reviews are typically lengthy. Whenever we give reviews, we simply don't say that we like the product or don't like the product, especially when we don't like the product. We write in length, paragraphs and paragraphs, why we don't like the product. So typically reviews are more than 100 words. And when we are building a machine learning model, we need to make sure that you have the sufficient amount of computational power and resources. In our proposed method, we try to tackle all these challenges. So our approach is going to be based on generative adversarial networks. So this is a brief overview on what GANs are. So I'm going to call it GANs. GANs are nothing but two neural network architectures competing with each other. You have the generator and the discriminator. Each one of them is a neural network architecture. The job of the generator is to generate data points or samples which resemble the real training data set. So you have the training data set, as I mentioned earlier. The generator tries to generate samples which looks very close to the training set. The job of the discriminator is to differentiate whether a given sample belongs to the generator or it comes from the training data set. Now what happens is that the generator and discriminator compete with each other, and that's why we call them as adversarial networks. The generator tries to fool the discriminator by generating samples which closely resemble the trained set, and the discriminator tries to differentiate between the both. Now, as they work in competition, the performance of the generator slowly improves. So that's how the generative adversarial networks work. And we are going to make use of these GANs in our approach. And GANs are predominantly used for images. In the last presentation, we saw how images are being analyzed, processed, and made use of in several different applications. And typically, GANs, a neural network based approach, is mainly used for image processing. It is used in applications such as image-to-image translation, image classification, image segmentation, etc. However, when it comes to text data, text processing, there are some issues with GANs. The first issue is the discrete nature. So whenever we deal with text data, the text is going to be converted into a discrete number. And why this is a problem with GANs? When you're talking about discrete numbers, the back propagation of gradients from the discriminator to the generator has some issues because the slight change in gradient cannot map to a particular word in the dictionary. However, this is not a problem with images because we deal with continuous numbers. The second problem when we are dealing with text data is the issue of sparse rewards. So let's say we are using GANs for text processing. In text processing, the generator of the GANs is going to generate sentences. Now you can judge the performance of the generator only by analyzing the quality of the complete entire sentence generated by the generator. You cannot judge the performance of the generator using a partial sentence or group of tokens in a sentence. So again, sparse rewards is a problem when text data is considered. Now we try and tackle these problems while using GANs with the help of a reinforcement learning approach, which I will be discussing in detail in the coming slides. Okay, so the approach that we have proposed and the one that I'm going to talk about is called as spam GAN. So it targets at spam posts, spam tweets, spam reviews. That's why I call it spam GAN. So essentially, spam GAN is a GAN-based method for text classification, though I'm talking about reviews, posts, and tweets. You can use it for any type of text classification. And the main highlighting thing about this approach is that it uses limited labeled data as well as unlabeled data. So it makes use of both types of data when training. So it not only uses labeled as well as unlabeled data. Remember, I told that the generator of the GANs generates samples close to the real data. So these samples serve as extra data points helpful for improving the classification performance. So this is just a recap of how our training data is going to look like. So we call them as real data. So our training data is going to consist of both labeled as well as unlabeled sentences. Labeled sentences in the sense that every sentence of the labeled data is going to contain a class label, whether it's spam or non-spam, like this. And every data point in the unlabeled data set is simply going to contain the set of sentences, the sentences being reviews here. Now, this is the architecture that we are going to follow for our proposed approach. The general GAN architecture contains just two components, the generator and discriminator. However, in our architecture, we have three components, the generator, discriminator, and classifier. This architecture was built gaining motivation from a method called CSGAN. However, our approach is different from theirs in the sense that we will be able to deal with longer sentences as well as we are computationally efficient. Now, like the traditional GANs, we have the generator and discriminator which compete against each other. The job of the generator is to generate sentences which look very close to the real data. And the job of the discriminator is to differentiate whether a given sentence is generated by the generator or it comes from the real data. Generator and discriminator work in competition. The generator tries to fool the discriminator, and that's how the performance increases. Though the generator and discriminator work in competition, we have another component called classifier for classifying the spam and non-spam labels. The generator and classifier work hand in hand. They are not competitors. They work complementary to each other. If the performance of the generator increases, the performance of the classifier also goes up. Now, specifically, this diagram shows how adversarial training takes place in our method. Now, what happens is that the generator generates sentences. Now, the generated sentences are passed to the discriminator and the classifier. The discriminator and the classifier scores these sentences. They give a score for these sentences based on how good the generated sentences are. Now, as you can see here, the score from the discriminator is QD, the score from the classifier is QC. Now, we combine the scores from the discriminator and classifier and we feed it back to the generator. So these scores are a form of a feedback for the generator to improve itself. If the sentences generated by the generator are good enough, which means they closely resemble the real data, then the scores are going to be high. If the generator has generated sentences that are not good enough, the scores are going to be low. So when the generator receives low scores from the discriminator and classifier, it will figure out that it's doing a bad job and it will try and improve itself. So this is the entire adversarial training process that we are going to adopt in our proposed method. I gave a brief description of how the proposed approach works. Now let me describe each and every component in detail. So the first goes the generator. The job of the generator is to generate sentences which closely resemble the real data. For that, the input to the generator is going to be the set of previous tokens. Now you can ask me why you need to give the set of previous tokens. By token, I mean the word in the sentence. Now, the generator follows an autoregressive generation process, which means it does not generate the entire sentence in one go. It generates the sentence token by token. First, it generates the token T1, then T2, then T3, so on and so forth. So for generating a token, it needs to know what are the previous tokens that have been generated. So that's why the previously generated tokens are given as input. Apart from this, we have the usual noise for the generator. We also give in as input the class label. So it's conditional generation. The class label is either going to be spam or non-spam. So when the class label is spam, the generator is going to generate sentences which look like spam. When the class label is non-spam, the generator is going to generate sentences which look like non-spam. Now, how does the generator know whether what is the pattern for the spam sentences and what is the pattern for non-spam sentences? That's what the generator is going to learn. So from the training data that is available, it is going to learn the distribution of spam and non-spam sentences, using which it is going to generate its own samples. So given the partial sentence, the partial previous tokens, the noise, as well as the class label as input, the generator is going to generate the next token in the sentence. Like for example, the next token that it generates here is token number 6. The hotel was airy and bright. That's about the generator. And as you can see, the architecture for the generator uses a recurrent neural network here. Like I told you, the generator, so this slide shows how the generator works. The generator generates the next token in the sentence. Now for that, you need to have the set of previous tokens, the noise, the class labels, and the parameters for the neural network. Apart from adversarial training, the diagram which I showed earlier, we pre-train the generator using cross-entropy loss between the predicted and the actual tokens. And the RNN architecture for the generator has 2 layers of GRU cells, each with 1024 units. Now the previous slide shows how pre-training works for the generator. I'm going to now discuss how adversarial training works. So for adversarial training, as I mentioned already, what the generator does is that based on the set of previous tokens, the generator generates the next token. The sentences generated by the generator are passed to the discriminator and classifier, which scores these sentences and gives some rewards. The rewards are then passed to the generator for it to improve itself. So this is the adversarial training process that happens in our approach. Now, the adversarial training process can exactly map to a reinforcement learning process. That's how we are going to tackle the problem of sparse rewards. So for the reinforcement learning process, the state is a set of previous tokens in the sentence. The action that is taken is the next token that has to be generated. The rewards that are obtained from the discriminator and classifier are given as feedback to the generator. So essentially, this is a reinforcement learning process where the generator is the reinforcement learning agent. The RL algorithm that we follow is an actor-critic, advantage actor-critic method, and we solve the generator using policy gradient. As I told you, the generator, the adversarial training represents a reinforcement learning process. Let's see what the loss for the generator is. The generator is trained based on the loss, which is the expected reward of a generated sentence. So what is the total expected reward for a sentence generated by the generator? Based on that, only the generator improves itself. So the expected reward is calculated using the scores from the discriminator and the classifier. So these values represent the expected reward. They are calculated based on the scores from the discriminator and the classifier, which I will be describing to you in the next 1 or 2 slides. So I told you we are going to see how the scores are obtained from the discriminator and the classifier. Let's first take the case of the discriminator. The discriminator scores the sentences. It can not only score the sentences generated by the generator, it can score any sentences. The sentences can come from the real data, or it can also come from the generator. Now, what is the basis of these scores? The discriminator scores the sentences based on how real they look like, which means how closely they resemble the real data set. If a sentence closely resembles the real data set, it's going to get a good score. Otherwise, it's going to get a bad score. So this is the scoring head, a neural network layer, which gives out the scores. Again, the scores are given token by token, not based on the entire sentence. Here, the scoring head gives the scores based on token by token. Let's say a sentence contains 5 tokens. All these 5 tokens are scored individually, and then you get the mean of these scores. So the discriminator has 2 types of scores. We saw one of the scores in the previous slide. We called that score as the Q value. There is also another type of score given by another layer of the discriminator called as the discriminator critic. We call this just as the value. Now these terms Q value and value are from the reinforcement learning paradigm. So to intuitively explain the difference between them, Q value represents how real each token in the sentence look, and V value represent how real the entire sentence looks. So that's the difference between Q value and V value. both of them will be used to generate the rewards. So in this slide, let me just tell you what the architecture of the discriminator is. It is a unidirectional recurrent neural network with one dense output layer. The discriminator is trained again using the traditional GAN laws. We have two terms, one for the real sentences and one for the sentences from the generator. The loss is formalized such that the discriminator maximizes the score on the real dataset and minimizes the score for the sentences generated by the generator. Now that's about the discriminator. Let's move on to the classifier. Like the discriminator, the classifier is also going to give scores for the sentences. Again, it can score any type of sentences, whether it is from the generator or whether it is from the real data set. However, the basis for the scores is going to be different from that of the discriminator. The classifier is going to give scores based on how accurately it can classify whether a given sentence is spam or non-spam. So that's the basis for the scores that the classifier gives. Again, it is going to give scores based on every token in the sentence, which are going to be averaged to give the mean. Again, like the discriminator, the classifier has two types of scores, one called the Q value and the other called just the value. So the Q value represents the accuracy of prediction with respect to every token in the sentence, and the V value represents the accuracy of, and the V value is based on the accuracy of prediction over the entire sentence. Again, the architecture for the classifier is a unidirectional RNN with one dense output layer. Like the discriminator, we have formulated the loss of the classifier here. It has different components for the data for the sentences from the real data and the sentences from the generator. The loss for the real data is based on the accuracy of classification. The loss for the generated data is not only based on the accuracy of classification, but we also add a regularization term, mainly because for the stability of predictions. Like I told earlier, we are going to combine the rewards from the discriminator and classifier, and then we are going to send these rewards as feedback to the generator. Let's see how we are going to combine the rewards. Now, these are the Q values obtained from the discriminator and classifier. We are going to combine them separately. And these are the V values obtained from the discriminator and classifier. We are going to combine them separately. And then we are going to subtract both these values, after which they will be sent as feedback to the generator. Now, how the Q values and V values for the classifier and discriminators are combined. So we are going to combine them in a manner which is similar to the F1 score. If you see here, this is the Q value from the discriminator and this is the Q value from the classifier. And this equation looks very similar to the F1 score. So that's how we combine the Q values for the discriminator and classifier and obtain the final Q value. Like the Q values, we also combine the V values from the discriminator and classifier and obtain the final V value. Now this final Q value and V value is what is going to be sent back to the generator. And if you see how the generator is optimized, the loss of the generator is based on the Q values and the V values obtained from the discriminator and classifier. So essentially, it is trained based on the expected rewards from these different components. And that's how these scores from the discriminator and classifier help in training the generator better. So this is in general how our approach works and the details of the different components of our approach. If you want to go into more details, please refer to our paper, which is given at the end of the slides. I'll point you to it at the end of this talk. Now, what we did was we ran experiments with whatever components that we have and with just what I described earlier. And in a small data set that we trained, we were able to achieve around 83 to 84% classification accuracy. And we also thought that there is some room for improvement, improving the classification accuracy. So what we did was we tried to make use of some of the state-of-the-art available pre-trained models. GPT-2 is a pre-trained transformer-based language model put forth by OpenAI researchers. There are different versions of GPT-2. We use the smaller version. The smaller version has 117 million parameters, and the parameters alone need 500 MB of storage space. This is a pre-trained model which has been trained on a massive 40 gigabyte dataset by OpenAI researchers. And as you can see in this figure, GPT-2 is nothing but a stack of transformer decoders, and we are using a stack of 12 transformer decoders in our approach. So I told you that we are going to use GPT-2 in our approach, and we are going to get improvement in our performance. So what is the major change that we are doing? So I showed you the earlier architecture where we are using recurrent neural networks for the generator. We are going to replace this recurrent neural networks using GPT-2. If you see here, this is the GPT-2 architecture. We've replaced recurrent RNNs with 12 transformer decoders. When we made this change, we were able to see a huge improvement in the quality of the sentences generated by the generator. The perplexity of the sentences, which measures the quality, went down by a large margin. So of course, we had performance improvement using GPT-2. We not only improved or changed the generator architecture, we also changed the architecture for discriminator and classifier. We replaced the recurrent neural networks in the discriminator and classifier using 12 transformer encoders. What we did was we fine-tuned these pre-trained models to adapt to our data set. And when we made all these changes, we were at least able to get an improvement of at least 3% in terms of accuracy. So let me quickly move on to the experiments. So we conducted experiments using a small data set at first. We used the TripAdvisor data set containing 1,600 samples, of which 800 are spam reviews, and we have another 800 non-spam reviews. As I told you, we are not only going to use a set of labeled data, we are also going to use unlabeled data. The unlabeled data is vast. We use 32K reviews as unlabeled data. We do a bit of pre-processing, as I mentioned here. We ran experiments with different percentages of labeled as well as different percentages of unlabeled data. So this is our approach called as SpamGAN. So 0% means we are not using any unlabeled data during training. It's a simply supervised learning approach. 50%, 70%, and 100% represents that we use 50% of unlabeled data, 70% and 100% accordingly, additionally during our training. So the 50%, 70% is the additional unlabeled data that we use along with the labeled data. We compare our approach SpamGAN with the state-of-the-art opinion spam detection approaches. And just to let you know, this is the previous version of SpamGAN. I've not shown the results for our SpamGAN approach with GPT-2. So these are the previous results. So this table shows the results that we obtain for SpamGAN for different sets of labeled data. I think it will be better explained when I describe this graph. In this graph, the x-axis represents the percentage of labeled data used during training. The y-axis represents the classification accuracy, whether the approach has correctly classified a given sentence to be spam or non-spam. The black color bars represent our proposed approach called SpamGAN. As you can see, when we have very little label data, so 10% of label data amounts to around 160 labeled reviews. With just 160 labeled reviews, you are able to achieve an accuracy of around 69%. Of course, our approach performs better than the others. And when we use 30% of labeled data during training, we are able to get around 80% classification accuracy. Of course, the performance of the approach, of all the approaches, goes up when you increase the number of label data, but our main contribution lies in this area. When we use very little label data for training, we are able to get better performance. That's the main contribution of our approach. So this slide shows the perplexity of the sentences. Perplexity represents the quality of the sentences generated. The lower the value, the better. Again here, the x-axis represents the percentage of label data and y-axis represents the perplexity score. And I have plotted the perplexity values of our approach when using different portions of unlabeled data. If you can see, the gray color line obtains the lowest perplexity, which means it obtains better quality sentences. So with more unlabeled data, we are going to get better sentences, better quality sentences. So these are just the results for SpamGAN. When we additionally use GPT-2, our perplexity decreases to a value of even 20 to 30. So we have a huge improvement in sentence quality when using GPT-2. So I need to talk about training time. The small TripAdvisor dataset on which we conducted experiments, it contains 1600 labeled data and 32K unlabeled data. We used the NVIDIA RTX 2070 GPU for training, and it took 3 hours to run one single experiment. That's for our original SpamGAN. When we improved our model, that is included GPT-2 in our model, replaced the RNN with GPT-2, it took 9 hours for training one single model. So that's just with a small data set. With a large data set, so we are conducting experiments using a large data set called as the YelpSip data set. It contains 80K labeled data and 80K unlabeled data. And it's taking around 22 hours for our previous model SpamGAN for training one single model. And around 66 hours, imagine 66 hours amounts to nearly 3 days for training one single SpamGAN plus GPT-2 model. So I should thank IBM for providing access for their AC922 machines. I believe with that, with these AC922 machines, we will be able to reduce the training times that I have shown here at least by 2 or 3 times. So that's in general the proposed approach as well as the experiments that we have. And to conclude, I've just talked about an approach for semi-supervised text classification. Semi-supervised because we use both labeled and unlabeled data. We get best results when the labeled data is limited and we outperform the state-of-the-art trust models. The state-of-the-art opinion spam detection models. For those of you who want more details about this approach, please look into our paper. This paper talks in length about our previous version of SpamGAN. And I'm also thankful to my team of students who are currently working on this project. So I believe that is the end of my presentation. Thank you all for listening patiently throughout my presentation.
Thank you, Professor Athirai, for the detailed presentation. It's very detailed, actually, and also thanks for, running your application on IBM AC922 systems too. Audience, any questions for Professor Athirai? You can raise your hands, or you can, I'll open up the chat window so that you can post your question on the chat window too. Audience, participants, also the panelists. Panelists, any questions for Athirai, Professor Athirai? Okay, I think Nandini would like to ask a question. Let me allow her. Go ahead, Nandini. Nandini? Do you have a question? You raise your hands.
I think Nandini, you are muted.
Yeah, Nandini, now it has been unmuted.
Nandini actually wrote the question in the chat box. So she asked, what is the accuracy of the model?
Okay. So,
And
so
where is it implied?
okay. Yeah, I can see the questions in the chat. So first of all, I believe there was a question about where did you get the data sets. So the data sets are publicly available data sets. We use the TripAdvisor data set, which contains 600 truthful or spam reviews and 600 spam and 600 non-spam reviews. These are publicly available. Yelp zip dataset, 80K dataset, again from it is publicly available, but you need to put in a request to their collector, and then you will get the dataset. So the accuracy of classification with respect to these datasets. For the TripAdvisor dataset, we achieved a maximum accuracy of around 84 to 85 with our old SpamGAN model, and around 89 with our new SpamGAN plus GPT-2 model. For the TripAdvisor dataset, we are currently having an accuracy of around 65-ish. That's the accuracy. Yeah.
Thank you, Athirai. Let me open up another question. Nalini, I'm actually opening up your.
Okay, so I can see some of the questions in the chat. Do you want me to answer them?
Yeah, go ahead, please.
Okay, so there was one question whether the dataset should be normalized or not. So the dataset that I deal with, especially in this particular application of GANs, it's text data. So what happens is that for the text data, we convert them into embedding vectors. So all that will be taken care of by the embedding vectors when we do training. So you're going to convert text into numbers or vector of real numbers, and that will be taken care of during training. Is the TripAdvisor dataset open accessible? Yes. If you look online, Google for TripAdvisor opinion spam dataset, you will get it. Size of the data, as I told you, there is a small, the TripAdvisor dataset is a small dataset with 1,600 labeled reviews. The Yelp zip, however, has 80K labeled reviews. Okay. How do you reduce precision error during training? Of course, there is going to be an error when you're training the models. You have to compromise with accuracy as well as computational power. And I also have a question on where to get medical data sets. So that's really a a huge problem here. So medical datasets are not prevalently available when compared to the text datasets. Usually, if they are available, they are highly restricted to hospitals and specific researchers who work together with the hospitals. And even though researchers, even for the researchers who use the medical dataset, the dataset is anonymized because you don't directly give out all the data about the patient. You anonymize the data and then share it with the researchers. Medical data is really hard to find.
Good. So we have another person asking question. Hold on. Let me see. I do not know why the tool is not working here.
Okay, I have a question whether I'm planning to use GAN for COVID-19 datasets. Probably not at this point. So COVID-19 datasets are in different forms. So one form, they have text data. COVID-19, there are different challenges for COVID-19. So some of the challenges simply use patient records, doctor notes, whereas some of the challenges use the MRIs and CT scans. You can use any approaches that you want. Specifically, GANs have shown better performance when dealing with image data. So if you're trying to use image data specifically for image generation or image translation, then GANs can be useful. If not, other machine learning models might be helpful when dealing with COVID-19 data sets, especially when it's not an image.
Yeah. Any more questions?
Okay, so I have one from Nandini. What are the applications for machine learning and neural networks? Of course, there are several applications for neural networks and machine learning. So let me give you some.
One second. Actually, somebody started talking. Yeah, go ahead, please.
Okay, sorry. So there are several applications of neural networks and machine learning. So a very simple example is your Facebook. Image tagging, you tag your friends, it automatically pops up a suggestion for tagging your friend suggestions. So those are examples of machine learning algorithm, especially deep learning algorithms, which are used in image classification. And then you have now self-driving cars like Tesla. So that's a lot of machine learning work inside Tesla or self-driving cars, which goes up. So now even the healthcare domain has started to use machine learning and deep learning technologies a lot, especially, for example, segmenting tumors. So using deep learning approaches for analyzing MRIs and CT scans and segmenting or figuring out where the tumor is in the image is going to be helpful for the doctors a lot, because doctors are quite overworked and these machine learning algorithms can aid them. I'm not saying that it's going to be a replacement. It is going to be helpful for them.
Thanks, Professor Athirai. Looks like there are a bunch of questions, people, continuously asking. Do you want to answer them, or do you want me to save them and send it to you later?
Yeah, I think, yeah, probably we can save them and we can, I can answer them offline.
Yeah, sure. That is wonderful. Thank you. And thank you again, Professor Athirai, for the presentation and for your time too. And thanks for all the participants as well as the panelists, for spending time here. And really, these two presentations are very useful for the people. And I'd like to, thank again, all the participants for all kindness and efforts to participate in this webinar from OpenPOWER POWER9 Academia team. Looking forward to meet you all on May 15th, our next webinar from Ohio State University and Nimbex, a cloud company. And these two talks are going to be related to AI as well as the cloud related workloads and other stuff. Thank you again. And I'm closing the webinar now. Thank you.